Right. For our course selected topics in decision modeling, today we are going to begin the nonlinear programming, and in this particular topic, that is nonlinear programming, today the first lecture, that is introduction. So, in the introduction is the first lecture that we shall have, and basically you see the nonlinear programming, first of all how it is different from the linear programming problem. That is a very basic issue that we should understand. There are certain assumptions, if you really recall, about the linear programming. What are they? The linearity assumption, then the additivity assumption, there was a constant returns to scale, and certain other assumptions. Out of all the assumptions, the first assumption, that is the linearity assumption, may not be valid for the nonlinear programming problem. Is it all right? So, the objective function or the constraints can actually may contain nonlinearity. What exactly it means? That they are not linear functions, that means they cannot be represented by straight lines. There are not first order constraints, but the objective function or the constraints, they can be higher order functions, is it not? May not be first order. Then there is this additivity assumption, which essentially says that decision variables may not hold in the objective function that or in the constraints. What happens in additivity assumption? Suppose we have two variables, that is x1 and x2, is it all right? So, what we are saying that x1 and x2, they are using a say common resource, is it all right? So, we have maybe the common resource is say 40, and we say that 2 units are taken by the first and 3 units are taken by the second per unit. So, therefore, we might put a constraint 2x1 plus 3x2 less than equal to say 40. Now, while we write this constraint, there is an inherent assumption that we can add 2x1 and 3x2, right. That means, they really consume the same resource and in that proportion, but supposing they just cannot be added in that manner, that means the additivity assumption is not holding, is all right. So, that could be another assumption that may not work. Then there could be constant returns to scale. So, when we write objective function, we write that maximize z equal to say x1 plus x2. Inherent assumption here that the profit per unit is x1. So, profit of 5 units will be 5. Suppose 1 unit is 1, then 5 units should be 5. But then sometimes we see that profit is something for 1 unit, but it might exponentially rise for more number of units. So, in that case x square is a better function than x. That brings nonlinearity as well. There could be other reason of studying NLP, that there are efficient algorithms are available for the NLP problems, right. So, having known this, let us look at another very vital thing about linear programming. Let us take a very simple problem. Maximize z equal to x plus y subject to here the x plus y subject to 4x plus y less than equal to 8, x and y both greater than equal to 0. So, what have we done here? Look here, we have drawn a line that is 4x x plus y equal to 8, and this side is 4x plus y less than equal to 8, and we have a solution space given by this. And the profit line, which is x plus y. So, you can see that actually x and y scales are different, x is 0 to 3, y is 0 to 10, that is why the lines are different. So, x plus y equal to 2, this is the line, x plus y equal to 5, this is the line, and x plus y equal to 8, this is the line. So, you can see that this line will cut at this point So, which is your the optimal point x equal to 0 and y equal to 8, that becomes optimal. In other words, the basic feasible solutions are essentially the corner points of the solution space. Here there are 3 corner points. So, there will be 3 basic feasible solutions, and the optimal solution is one of the corner points. Since the optimal solution lies at one of the corner points in the linear programming problem, that is the advantage. The basic advantage of linear programming problem is that the solution lies at one of the corner points, right. So, we have to search finite number of points. Once we get the solution space, there is no need really to worry anymore, and we just explore those corner points, the feasible corner points, or sometimes called basic feasible solutions, and we know one of them is going to be our optimal solution. That was a very basic advantage of linear programming. Let us see what happens in nonlinear programming. The problem is same, but objective function is different. Earlier we had x plus y, now here if you see, the objective function is x star y, right, not x plus y, subject to 4x plus y less than equal to 8 and x and y greater than equal to 0. The problem is same. Since the constraints are same, the solution space is also same. So, it is the same solution space between 2 to 8, the line, that is 4x plus y equal to 8, and the objective function x y. See, this is the x y equal to 1 line, this is the x y equal to 2 line, and this is x y equal to 4 line. So, if you look that the x y equal to 4 line just touches, actually this line 4x plus y and this x y equal to 8, x y equal to 4 just touches at a point, and that is our optimal point, because if I take any lower value of x y, maybe x y less than equal to 4, less than 4, then obviously it will be the lower objective function value, but any higher x y value will be not touch the solution space at all. So, therefore, that is our optimal point. The optimal point is then x equal to 1 and y equal to 4. Now, if you carefully see, then this point is is not a corner point. So, that is the basic point to note. Even if we have only one variable, only the objective function is non-linear. Look here, the constraints are still linear here. The objective function is non-linear. The optimal point actually does not lie on the corner points, right. So, the basic advantage that we have of the linear programming, that our search space was finite, we see only the corner points, that advantage is gone, right. So, the basic advantage of linear programming is not available in nonlinear programming. So, you can understand that the solution space, the solution methodology has to be different. We just cannot use the standard linear programming methodology for solving nonlinear programming problems. Sometimes even we might have the solution when we might be having constraint lines which are also nonlinear. Maybe the optimal point may be within the solution space, may not be on the boundary also. Is it all right? So, all kinds of things may be possible then. The optimal solution could be a corner point, optimal solution could be a point on the solution space boundary, or it can also be within the solution space, right. So, infinite number of points are now candidate solutions instead of finite set of corner points, what was our advantage in linear programming. So, these are another very important aspect that we should also be aware of. So, the applications of nonlinear programming are applicable to all problems wherever we encounter nonlinearity. Truly speaking, almost all the linear programming problems, with a little variation there could be nonlinearity. Just take a very simple transportation problem. We have the cost function, which was usually we take Cij, cost per unit transportation, but supposing the cost is not linear, right. For one unit the cost is something, but for more units cost is not proportional. We have a nonlinear problem. So, in any situations wherever we have applied linear programming, we must remember that those are actually special cases. The general case can be a nonlinear programming problem. Now, objective function can be nonlinear, constraints can be nonlinear, and or objective function constraints both can be nonlinear, right. So, those are the possibilities of the NLP problem. Now, broadly we may classify the nonlinear programming problems NLP into these 4 different classification, actually not 4, actually 2. The problems could be unconstrained or constrained, or problems could be convex or non-convex. Is it all right? So, there could be unconstrained problem, as the name suggests that there are no constraints, there is only objective function. The constraint optimization, on the other hand, there is an objective function and there are constraints also. Is it all right? Those problems will be more complex, whereas if we have unconstrained optimization, we only have one function, that is the objective function. But on the other hand, there could be convex programming and the non-convex programming, that will depend on the type of functions that we are encountering. So, that is how we can have different types of nonlinear programming problem, and there could be other variations as well. So, all of those variations we shall study as and when we get those kind of problems. So, let us look at an unconstrained optimization problem. So, we have objective function which is nonlinear and there are no functional constraints. So, here are some examples: maximize f x1 x2 equal to 2 x1 plus 2 x1 x2 minus x1 square minus 2 x2 whole square, 2 x2 square. So, see, this is a nonlinear function, but there is no constraints. So, that is an unconstrained optimization problem. So, similarly, you can also have a 3 variable problem, x1 square plus x1 into 1 minus x2 plus x2 square minus x2 x3 plus x3 square plus x3, etc. So, these are all unconstrained optimization problem. The unconstrained optimization problem, so the constraint on the other hand. So, here if you look at, this is not an unconstrained. So, there is a this has to be this is not unconstrained. So, we cannot, so we can cut this part. So, this is a constraint optimization problem. So, the constraint optimization here we have a minimization function and subject to there are some constraints. So, we have a constraint here and that could be a minimization function. So, if we plot this curve, then you can see that these x versus f x, this plot is given, and this particular function actually can look like this. So, that is a constraint optimization problem. Now, let us look at another problem, that is the constraint. This is, there is another problem, that is a constraint optimization problem. So, what really happens here, subjected to functional constraints. So, both objectives and the constraints can be nonlinear, right. So, when objective functions and the constraints both can be nonlinear, we have a constraint optimization problem, right. So, there are constraints and unconstrained optimization problem. So, let us look at a constraint optimization problem. So, see this constraint optimization problem, if you see that here this is the function is 2x1 plus x2 subject to these constraints, and this is the plot, and see this actually this is the xy plane, the fx is plotted on this. So, you can see since it is a minimization function, we have to really see that this is our solution space. So, within this solution space the functions which is the minimum value of this function, right. So, that is what we have to see. Incidentally, this happens at 0 probably, but anyhow that is a particular problem. So, we might have a objective function which could be maximized or minimized, and there are a set of constraints. So, we can have the solution space is in the xy plane, but the objective function which is separately shown by the fx function. So, where we have the minimum fx value within the solution space. So, you can see that this is different from the way we deal our linear programming problem. The considerations are very different here. So, these are other examples of constraint optimization problem. So, you can have a minimization problem where fx is x1 minus 2 whole square plus 2 x2 minus 1 whole square subject to certain constraints, or we can have an ln function ln x1 plus 1 plus x2 subject to certain constraints. So, you can have several types of unconstrained and constraint problems. Now, a very important consideration is the convexity and concavity of functions, right. So, as you can see here, there are two examples, concave functions and convex functions. The concave functions are curving downwards, whereas convex functions are curving upwards or not curving at all. So, in that sense a linear function can be considered both as concave as well as convex, right. So, because neither they are curving downwards nor they are curving upwards. You see, a very important thing to note that if we have a maximization problem, the maximization problem will have a maximum point. So, you can see this concave function, these kind of functions where you can find out the maximum of a variable, whereas the convex function you can have the minimum of the function. You cannot have a maximum value for the convex function by differential method. So, what is the differential methods? Let us see that. So, supposing if we find suppose we have the function as fx, right, and we find what is known as df dx, dfx dx, that is the gradient, right. So, what is the method? Method is that we put gradient equal to 0, right. So, if we find gradient equal to 0 to find optimal, that is x star. So, we find the gradient equal to 0 to find x star, but there is a point, the point is that this will be, and suppose we have a maximization problem, then additionally we have to take what is known as a second derivative. The second derivative should be negative, right. For a maximization problem, the second derivative should be negative, that is the point to be noted. Whereas so you can see that really if you are having a maximization problem, then your function should be concave, objective function. On the other hand, for a minimization problem, so minimization, we have again dfx dx equal to 0 for optimal x star, but to note that we must have the second derivative should be positive, right. So, these are some of the considerations that we must have for the convex or the concave kind of functions, right. So, therefore, we must have that kind of consideration. So, that is what we say, that for concave functions second derivative must be negative and a global maximum should be possible to have. So, just now I explained that for convex functions second derivative must be positive and a global minimum should be possible to have. Is it all right? So, by taking a suitable second derivative, we can find whether it is negative or positive, and we may find therefore the maximum or minimum of a function by such considerations. Now, sometimes the curve could be something else. So, you see if you look at this curve, is it going down or going up? So, it is very difficult to tell. So, it is neither convex nor concave function. So, here if you find derivative, what may happen, you may actually find the, so this, suppose these points, you see they are local maxima or minima. So, for such kind of problem you might find local maxima or minima, and you may not be able to find the global maxima so easily, right. So, that is why the convexity and concavity of the functions are so important. So, then we might have to use some other methods like evolutionary computing, right. So, therefore, we see that convexity and concavity are very important considerations, particularly for maximization problems concavity is important, and for minimization convexity is important. Now, that brings us to the convex programming. Essentially, if we have a nonlinear program to become a convex program, we must have two things. Number one, the objective function should be a concave function and each constant should be convex. Convex means it could be linear also, because linear is both convex and concave. So, objective function should be concave. Now, when you see this particular maxima is f x equal to say 5 x 1 minus x 1 square plus 8 x 2 minus 2 x 2 square, how do you know it is concave, right? All that you know that if I take its second derivative, then the second derivative should be negative, right, because it is a concave function. Now, let us take a very simple case. Supposing our f x is only this much, f x is 5 x 1 minus x 1 square. So, what is the first derivative? First derivative will be 5 minus 2 x 1. What is the second derivative? Second derivative will be minus 2, right. So, this is negative, which means that this portion is concave, right. So, you can similarly take the second part also, like, so we have taken the first part, we can also take the second part, and suppose we take another function f x equal to 8 x 2 minus 2 x 2 whole square, then we find f dash x, that is the first derivative, will be equal to minus 4 x 2 and f double dash x becomes minus 4. So, you see, so this is also negative. So, we find that that is also concave. So, now an interesting thing is that if I can partition a particular function into separate portions and I can show that this is concave and this is also concave, then that means the total function is also concave, is all right. So, that is how you can also do, but then this is very typical, not very simple process. So, we have to solve such problems as and when we find them, right. So, that is about the convex programming. So, you see the same problem again, I have plotted the function. So, if you look at the plot, then you can see that basically it is a convex kind of function, is it all right. From the nature of the plot, you can find out that this is actually a convex concave function, is it all right. So, we find that the f x is actually concave, right. Since f x is concave, it is possible to find what is known as a maxima, there will not be any difficulty, right. So, having said that, let us now see other examples. So, for example, minimize f x equal to x 1 plus x 2 plus x 3 plus x 4 and subject to all these constraints, or minimize minus 2 x 1 plus x 2 x 1 plus x 2 whole square x 1 square plus x 2 whole square greater than less than equal to 3. So, there could be several examples of these kind of thing. So, like this is a maximized thing. So, these are other examples. So, here is another example of convex programming. So, this is the plot that is shown here. The non-convex programming, usually it is the convex programming and the non-convex programming. So, in non-convex programming, the those two constraints that we have had, that is the objective function is a concave function and each constraint is convex, they may not hold. So, when any one of these conditions are not satisfied, we have what is known as non-convex programming. For example, suppose f x equal to x 1 x 2 and these are my constraints. So, what we may have if we plot, then let us see one such example. If we see an example, this example we have already seen that maximize z equal to x y and 4 x plus y less than equal to 8. You see the objective function is convex, right. Since the objective function is convex, we have the objective function concave, that is not possible. So, therefore, it is a non-convex programming. So, since objective function is not a concave function, although the constant is convex because it is linear, but then we call it a non-convex programming. Then we have what is known as the quadratic programming. The quadratic programming is similar to linear programming, except that while the constraints are linear, the objective function actually contain quadratic terms, like see like x 1 square. So, you can see that we have the square terms and we have the product terms. So, when we have such kind of terms, we actually call them quadratic programming. So, quadratic programming has got their own methods of solving, which we shall see in due course of time. So, here is another example. Such kind of examples, again you can see that there are the square terms or the product terms. So, when you have such situations, we call them quadratic programming, all right. There is another type which is known as separable programming. What happens in separable programming? If the objective functions or the constraints are having multiple variables, but they are actually can be separable in terms of individual decision variables. So, here is an example. So, supposing this is our objective function. Now, you see, so maximize z equal to f x. Now, which is basically is a function of two variables. Maxima is z equal to f of x1 and x2, which is possible to write gx1 plus hx2, right. So, what is gx1 here? Gx1 is 126 x1 minus 9 x1 square and hx2 equal to 182 x2 minus 13 x2 square, right. So, you can see even this one, the constraint, this is only x1, this is only x2, this is 3x1 and 2x2, they can be separated. So, when you can do such separation into functions of individual variables, then those kind of programming are called separable programming. So, we shall see later on how such kind of problems could be solved, right. So, leave it here. In this particular lecture, we introduced various types of nonlinear programming problems, right. Thank you very much.